welcome to the class. We have till time covered the portion of different turbines where different aspects of axial turbine, rather where we had seen mainly the axial turbine can be of impulse type or reaction type depending upon the degree of reaction. Then we covered some design aspects of the axial flow turbine. Now after covering the part of the axial turbine, we will just have a very brief look at the other type of turbine, which is radial flow turbine, and then we will solve a typical example for the case where we are going to see about the axial flow turbine in through the example, the concept of axial flow turbine through the example. About the radial flow machine, in one of the earlier lectures, rather very first lectures, we had seen that the turbo machines can be of two types, one is axial and one is radial. So we had seen in similar line so axial flow compressors and centrifugal compressors. So there was an entity called as centrifugal compressor, which was the outward flow machine where the fluid was coming through the eye of the impeller, and then it was going outward, and then while going outward it was gaining the work which was through the impeller, and then it was going to the volute casing. So that was the idea of centrifugal compressor. Then we moved toward the axial compressor where the flow is going through along the axis of the compressor. Now same way as we had axial flow compressor and radial flow compressor, which is centrifugal compressor, we have axial flow turbines and radial flow turbines. So in the radial flow turbines, unlike axial compressor where we had a flow which is going outward, we are having which is flow coming inward. So inward radial flow turbines so are generally worked out in the compressible flow regimes. So the gases generally have inward radial flow turbines. So in the inward radial flow turbines, as we can know, there will be again inward flow coming through the volute, and then we have here is the volute, and then we have the flow after volute will come through the nozzle. Once it passes through the nozzle, it will come into the casing, and then after passing through the casing it will go to the diffuser, and then it will go to the exhaust. So these are the different components of radial flow turbine. So you can see that flow is inward, it is coming along the radius toward the center of the circle. So it is like inward toward the center of the output shaft. So the parts which were having functions in the centrifugal compressor exactly would have inverse function in case of the radial flow turbines. So here initially we have nozzle, which were earlier in case of centrifugal compressor were diffuser vanes. So nozzle would initially convert the high pressure to the necessary kinetic energy here in the part which is called as nozzle. So after passing through the nozzle, the flow which was at high pressure at the entry to the nozzle would turn out to the high velocity at the exit to the nozzle, and then the flow passes through the turbine blades. So here we can see that the turbine would rotate, and then the enthalpy drop necessary required for the work output would be taking place into the turbine, which is impellers again. So turbine blades here would again be impellers. Then there will be certain amount of kinetic energy at the exhaust to the turbine or at the exit to the impeller. If that is very high, then there will be diffuser blades, there will be diffuser which will reduce that kinetic energy to the required energy at the exhaust of the complete radial flow machine. So this is general configuration of the radial flow turbine, and then the TS diagram would be as similar as that earlier case where we will have isentropic expansion in the nozzle, and then we will have again expected isentropic work into the work interaction into the impeller blades. So there will be, since nozzle is non-work interacting part, so there will not be any work interaction over here, but in case of impeller blades we will have work extracted, so total pressure decreases when we come from 2 to 3, but total pressure would partially decrease from 1 to 2 since we are having loss due to friction, but total pressure decrease or total temperature decrease between 2 to 3 is mainly due to work interaction and partially or very small amount due to losses. So this is how we would have the TS diagram for 1 to 3, but 3 to 4 is again a diffuser. So in case of diffuser we have again no work interaction, so we will have partially the loss in total pressure due to friction again. So this is the gross perspective of the radial flow machines, radial flow turbine. As we have seen that axial flow turbine is very compatible and generally preferred for aircrafts since it has lesser drag for a given diameter, but here as we go for higher pressure ratios, the diameter needs to be increased for the axial flow compressor or axial flow turbine, so their drags are higher, so these machines are not generally preferred, but the fact is the per stage work interaction is higher in this case, so these can be preferred if we are working with lower work output of the turbine. So this is how we have the typical radial flow turbine composition and aspects of typical radial flow turbine. Okay. So after this we will see an example for the typical turbine case, and then example reads like an axial turbine has following data at the mid height of the blade. We should remember this example is purposely chosen for the fact that we had seen something which is called as the radial equilibrium and free vortex theory. So this example is based on that free vortex theory and radial equilibrium. It helps us to understand different concepts. So at the mid plane of the height, so blade is we know that typically this is a turbine, so we have blade over here, this is a stage, so we would have first nozzle, and then we have blade. So this is blade. So this is the typical configuration of a stage in case of the axial flow turbine. So this is how the flow moves along the axis, and this is the hub where it is mounted. So what we are given is at the mid height, so this is mid, and then we are told that the nozzle exit angle, which is alpha 2, is 75 degree. We are again told that blade entry angle is beta 2, which is 45 degree, and then we are given that blade exit angle, which is beta 3, which is 76 degree. So these things are given at the mid height. Okay, but apart from that we are given that the diameter, hub diameter DH at this DH is 450 mm. We are told that then tip diameter DT is equal to 750 mm and N is equal to 6000 RPM. So this is something which is given to us. Here we are not told about the height at the mid plane. So we can find out the height at the mid plane from this data, where we can say that dm, diameter at the mean, is equal to half dh plus dt. So dm is equal to half, dh is 450 plus 750 in mm. So now at the mid we are also knowing that what is dm in mm, but then we know that u, which is the rpm, which is the velocity, tangential velocity at the mid plane, um is pi dm n by 60. So we are knowing n, we know dm, so we can find out um. So these things are given. So further it is told that assume free vortex theory and determine following things at hub, mean and tip of the blade. So we are asked about degree of reaction r, we are asked about angles, okay, relative and absolute velocity angles, and specific work output. So we are asked about these things. So having known this, we will proceed with the example. So before that we should first draw the velocity triangle, and then I will describe how we are going to solve this example. So for the gas turbine, axial gas turbine, we have seen that this will be our typical velocity triangle, where we have here C2, this is V2, this is U2, and we say that we are drawing the velocity triangle at mid plane height, we are drawing the velocity triangle. So this is CA and this is we are drawing at mid plane, mid height, and then this is, for all sake, this is CW2, okay, V2, U2, this is CW2. We know that this angle is beta 2 and this angle is alpha 2. So similarly, then if we go to the outlet velocity triangle, then for outlet velocity triangle, this is V3, this is C3, and then we have this as alpha 3, and then this as beta 3. So this will be CW3. So this is what the velocity triangle as what we had seen. So now we have to find out everything at mid blade height. So at mid blade height we have found out, we are rather given with alpha 2, beta 2 and beta 3. We just have found out what is u, so we just have to find out what is r. So for r we know formula for r, which is Ca upon twice u into tan of alpha 2 minus tan of beta 2. So this is the formula for the r, which is degree of reaction, but we don't know Ca. So we can find out Ca here by using the formula u is equal to Ca into tan of alpha 2 minus tan of, one second, formula for r is u Ca upon twice u into tan of beta 3 minus tan of beta 2. This is the formula for r, but we need to find out Ca over here, and Ca can be found out from formula which is tan of alpha 2 minus beta 2. We have derived this formula from the velocity triangle itself, where we had seen that degree of reaction is enthalpy drop in the rotor divided by total enthalpy drop in a stage. So from that we have derived this formula. Further, this u by u is equal to Ca into tan of alpha 2 minus beta 2 can be found out from this velocity triangle again. So we get Ca is equal to u divided by tan alpha 2 minus tan beta 2. So we know u, which is found out from pi dn by 60 for mid, So you have to take mid height over here and find out this. We know alpha 2, we know beta 2, so Ca can be found out. Once Ca is found out, we will put this Ca over here and then we will find out what is R. So R can also be found out. Since Ca is known, U is known, beta 3 is known, beta 2 is known, we can find out. So we need to find out just work interaction. So for work interaction, the known equation is U into Ca into tan of beta 2 plus tan of beta 3. So specific work interaction at the mid plane height is U is known, Ca is known, beta 2 is known, beta 3 is known, then we can know W. So by this formula we can find out everything at mid plane height. But our objective again here is to find out all these things at the tip and the hub also. So let us find out these things at hub. So for that we have to use the free vortex theory. As per the free vortex theory, we know that Cw into R is equal to constant. This is what free vortex theory derivation we had seen. Further, we are saying that there is radial equilibrium. Once we have radial equilibrium in exist and free vortex theory, we can also take that Ca is equal to constant in the complete stage. So we will take Ca is equal to constant. This is known to us, we take it to have no axial thrust, and then we are knowing that Cw2 into R2 is equal to constant. By all these means, we mean Cw2 into R2 for the mid is equal to Cw2 into R2 at hub. So we know that what is Cw? Cw2. Cw2 is basically is equal to Ca into tan alpha 2. Ca into tan alpha 2 into R2 at mid is equal to Ca tan alpha 2 into R2 at hub. But Ca is constant, so we have R2 into tan alpha 2 corresponding to mid is equal to R2 into tan alpha 2 corresponding to hub. So we can find out tan alpha 2 at hub is equal to 1 upon R2 at hub into R2 into tan alpha 2 at mid. So at the mid height we know R, which is dm by 2, alpha 2 is known to us, which is given to us, and then height, which is dh by 2 at R, which is also known to us. So we know basically alpha 2 corresponding to the hub diameter, at the hub diameter. So we know that. Now knowing this, we can proceed with rest of the things. Further, since we know this, we also know Cw2 at mid, Cw2 into R2. This equation gives us alpha 2 at hub. Cw2 into R2 at hub is equal to Cw2 into R2 at mid. So at mid we know Cw2, at mid we know D2. So from this equation we know Cw2 at hub. So this is also known to us. Now we can proceed with these things. Further, for that we should know U at hub is equal to pi dh into n by 60. So by this we know what is U at hub. So we can use this formula where we have to say that this is at hub, this is constant, alpha 2 at hub and beta 2 at hub. So we should know what is beta 2 at hub. So for that we can use basically this formula to find out beta 2 at hub. U at hub is known, Ca is known, alpha 2 is known, so we can find out beta 2 at hub using this formula. Rather, this formula can help us now in finding out beta 2 at hub. Now our objective is to find out R at hub and W at hub. So for R at hub we should know beta 3 at hub. So for finding out beta 3 at hub we can carry forward the same method of calculation, which is CW 3 into R3 at hub is equal to CW3 into R3 at mid. So then we will have CW3 R3 at mid, CW3 into R3 at mid is equal to CW3 into R3 at hub. So at hub we know that, okay, so this is one thing. So we need to find out beta 3, so we can say that UCA into tan beta 3 at hub. We are doing it for hub, but velocity triangle can be similar. So we will say CA into tan beta 3 at hub is equal to CW3 plus U2. So basically this is what CA tan beta 3. So we have tan beta 3 is equal to CW3 upon CA plus U2 upon CA. So this U2 is found out by us. So we have tan beta 3, which is CW3 into R3 at mid divided by R3 at hub into CA plus U2 upon CA. So we know this, we have calculated everything at the mid. So we know this, we know this, we know this. U is pi dn by 60 for the hub, and then we know CA, so we know beta 3. So knowing beta 3, we can use this formula R is equal to CA upon twice U into beta 3, tan beta 3 minus tan beta 2. Here beta 3, beta 2 corresponds to hub now, and then we know this U is also corresponding to hub. So we can find out R at hub. Similarly, we can use formula which is W is equal to U into CA into tan beta 2 plus tan beta 3. So here U at hub is known, CA is constant, tan beta 2 at hub is known to us, and then we know tan beta 3 hub also. So knowing tan beta 2 and tan beta 3 at hub, we can find out the W, which is work interaction at the hub. So this whole procedure is based on the fact that we know everything at the mid. Once we know everything at the mid, we can proceed and find out the things at the hub. Similar thing can be repeated for the tip also. So we should know first diameter at the tip, which is known to us. Once we know diameter at the tip, we can find out U pi d. U is equal to pi dn by 60. So U2 will be known to us at the diameter of the tip, and then we can use the free vortex theory, where we will say that CW2 into R2 is equal to CW2 into R2, corresponding to mid and corresponding to tip. So then we will find out alpha 2 using that. Since we know that, as we have seen over here, R2 into tan alpha 2 is equal to R2 into tan alpha 2, corresponding to mid and tip. So we can find out tan alpha 2 at the tip. So once we found out tan alpha 2 at the tip, we will find out tan beta 2 at the tip using the formula U upon CA. Okay, so that will give us tan beta 2. So then we have to find out tan beta 3. So tan beta 3, again we will use same formula CA, tan beta 3 is equal to CW3 plus U2. So everything would be repeated for the tip. So this is how we can solve an example in case of an axial turbine. Okay, so this lecture which dealt with the calculation for the axial flow turbine, or rather in case of turbine, and specifically some discussion about the radial flow turbine ends here, and then in the next class we will see about the other components of the gas turbine, which would include as intake and the nozzle. Thank you.